Okay, so we'll start with the MOS transistor large signal modeling. And so this is just a very rough, some of you probably have already done layouts for transistors. So, usually you put this, what's called a diffusion layer, right? And then you put a poly layer on it, which is your gate. Poly layer, which is the gate. And this is really your top view, right? This is what it looks from top view. And if you look for a 3D view of that, that's how it'll look. Okay, so you have an N plus region, which is either a source or a drain. And the reason it can be source or drain, because it depends on the bias. So they have another N plus region, which can be source or drain. And that's probably one of the most important thing to remember is that this device is actually very symmetric in the sense, like in BJTs, for example, when you draw BJTs, you have a collector, base, and emitter, right? Now this is actually fixed in the device. You cannot interchange collector and emitter. You cannot do that, right? But in a MOS, you can do that, and I'll show in a little bit. Some of you are probably aware of it. Now, if I just do a cross section of this, right? You usually have what's called a substrate, right? And that's your main wafer. The entire wafer, like a giant wafer, is something called a P minus substrate, right? And then you have this N plus region, then you have another N plus region, and then you have what's called a thin oxide, and that's a very thin oxide layer. And on top of that, you have polysilicon as a gate, right? So that's your gate, and this could be either drain or the source. Same here, this could be either the drain or the source, depending on the bias. Now MOS, if you remember, it's a metal, oxide, and semiconductor. So you got oxide, you got semiconductor, but this is not metal, this is polysilicon, purely because of processing reasons, right? So people would love to have this metal, but it's very difficult to make it metal. So that's why it's called, and that's the reason why it's called metal MOS transistors. Now the symbol we're going to use throughout for this project is this symbol here. So it's actually a 4-terminal device because you have this P substrate, which is usually connected to your lowest supply, but usually you have something called a P plus connection here, and that's how it's connected. It's not connected from the bottom of the substrate, but it's actually connected. There are many, many connections from the top of the substrate, although it's the same substrate. And once we start doing projects, we'll know better. And this is usually called the bulk connection. So you have really 4 terminals, right? You have got one drain or a source, gate, another drain or source, and bulk. So you have 4 terminals. Now, usually when you bring the symbol in a cadence, for example, so that's obviously your gate, but this symbol tells you that if it is an N channel and this is your arrow, this is usually the source and this is the drain. But that doesn't mean that it is drain and source. It actually depends on how you bias it. And then usually the bulk will annotate it by putting a middle connection. A lot of times when we're doing circuits, we actually would just omit this for clarity. And usually that means it's connected to ground or the lowest supply, right? Or it's connected to the substrate, the source terminal. So in an NMOS channel, usually the gate to source is a positive bias. So your gate with respect to source, which is usually called VGS, that's actually positive. And your drain with respect to source is also a positive terminal, right? So that's your, that's typically how you'd bias for it to function. So VDS is greater than 0, VGS is greater than 0, and the bulk, like as I said, usually is connected to the source or to the lowest supply. Lowest supply here. And again, I want to repeat that this drain and the source terminal are just the way they are biased. Like for example, if you bring the symbol in cadence, but you actually put opposite bias, you put a negative bias here and a positive bias here, this is actually source, this is drain. All the symbol still shows that, but the symbol doesn't know. So, okay, so you have to always be aware of that you bias it properly. Now, another thing I just want to quickly show is that because this is a N and this is a P type, you actually have a parasitic diode between the substrate and the drain and source junction, like that, right? So if I draw again the symbol here, so you have the gate, and let's say we show the arrow, that means this is denoted as a source, this is denoted as the drain. So you actually have a diode between these two, and that's your bulk connection. So because of this, this is a parasitic diode, obviously. It's unintentional. And because of this diode, you want to always make sure, like as I said, the bulk needs to be lower than every other supply in drain or source. So compared to the drain, it should be always negative. Compared to the source, it should be always negative, right? Otherwise, you don't want this diode to go forward bias. Then your device won't function the way it's supposed to be. So typically, this is always put to the ground supply. That's the lowest supply, 0 volt. So that way, whatever these voltages are, it doesn't matter. It is always reverse biased. If the source or drain is ground, then it's fine. If it is not, it's still reverse biased. And I'll show you the just an equation showing what's the effect of having a voltage of the bulk with respect to the source in a later slide. All right. And you don't have to take notes. You just try to listen, because I'll put this up notes. If you just want to take like some few basic notes, that's fine, but don't have to write everything. Okay. It's more important you just listen. Okay, so now a PMOS transistor. So PMOS is actually the complementary version of NMOS. So it's the same thing again. So the substrate is still the same. So you have same P minus substrate, right? P minus substrate. But since now we're trying to do a PMOS, we actually need an N-type substrate. So what we usually do is we'll do a well. We'll do a big well, and that's usually called your N well. And that's basically a N minus substrate. And then your source or drain would be a P plus type. You'll have another source or drain as P plus type. And then like before, you have that thin oxide layer. And then you have the polysilicon gate. And that's your gate connection. That again, same way as the NMOS, is either can be the source or the drain, depending on the bias. And that's your gate connection. And again, for the substrate, which is the N well here, you usually have another N plus connection, which is your bulk connection. Now the symbol we're going to use for the PMOS is this symbol here. And the bulk will be again connection between this. Again, if this arrow is shown here, it usually means source, but it depends on how you biased it, right? So just like the NMOS, it doesn't physically have a source or drain connection. It's how you bias it. Now with the PMOS, it's exactly the complementary of the NMOS. So the source is actually needs to be always positive bias with respect to the drain. And the same way, the gate or the source again needs to be also positive. I'm sorry, the drain needs to be a positive bias. Source needs to be a positive bias with drain, and the source also needs to be a positive bias with gate, or in other words, the gate with respect to the source. So if I write the same way as before, VGS now needs to be a negative voltage. VDS, this is drain to substrate, source, also needs to be a negative voltage, right? And in case of the bulk, it needs to be put to a highest voltage. So typically this is your VDD in a supply. So let's say these nodes are something else, like if you have a switch, then the bulk is connected to VDD to make sure that similar like NMOS, like for example in NMOS, and switch here. Like in NMOS, it's too thick. All right, just like in NMOS, you have a source node. Again, repeat, there is no physical source node. It's how you bias it. But once we represent it this way, we make sure you bias this node, which is higher potential than the drain node. That's the only way it becomes. So if you switch the potential, the current is going to flow in the other direction. So just like the NMOS case, there is a diode here, which is the opposite type of diode here. And this is again a parasitic diode. So if you have a bulk connection here, you're going to get this diode between the bulk and the source. And again, you're going to get a p-type diode between the drain and the bulk. And because of this diode, you always want to make sure that this node is always positive with respect to this drain here. Same way, you want to make sure that the bulk is always positive with respect to negative node also. And that for that reason, this node is usually connected to your highest supply, right? Which usually we call it as VDD. Or it could get connected to the source. But if your V source to bulk is not equal to 0, then you have effect on the threshold voltage, which I'll come to a little later. And a lot of times you also write VSG as greater than 0 and VSD greater than 0. You just reverse the polarity basically. Reverse the polarities between these two guys. It's up to you how you decided. For the longest time, I actually preferred just writing the magnitude of it because it, made it more clear writing it that way. Okay, so now let's look at how the MOS transistor functions. So just showed you a physical picture of it. How does it function? Just close this right here. Okay, so this is the same transistor again. So, like I said, the source here is typically source is source, but since both of them are so grounded, it can be either source or drain because there's no current flowing through them. So you have the oxide layer, that's your poly, and that's your substrate, right? So here it's functioning as just a two-terminal device. So if I just show the diagram again, you have the gate here, the drain, source, and bulk, they're all connected to ground here. And then I'm going to initially put a negative supply here, okay? And if I put a negative supply here and look at the charge formed here, so this is a P minus substrate, which means that the majority carrier here are holes, right? So if I start putting a negative voltage here, that means there will be more negative charges here, which will accumulate more positive charges here, which means that this will make it more P-type. And if it makes it more P-type, basically you just look like a capacitor here. So it's like a capacitor, and the drain and source are isolated. The reason they're isolated is because you have this depletion layer in between, right? So essentially what it looks like is this back-to-back connected diode. And then so there will be no current flowing through it. So all it looks like is a capacitor between the gate and the bulk. And then you have this between drain and source, you have this back-to-back connected. This is between drain and source, right? And there is obviously no current flowing here. So it just looks like a capacitor. And this capacitor is typically, value of Cox times the area of your transistor, where the Cox is your relative permittivity epsilon naught over the thickness of the thin oxide. But actually it's a little bit more complicated because you have actually depletion capacitor also, but we'll not go into that because this operation, which is called the accumulation region operation, we actually never use in this. Rarely we ever use in this. So it's just good to know, but you don't need to know anything more than this. Okay. All right. So now let's look at the same capacitor, but I mean same transistor. We'll have the same configuration again. Sorry. Hmm. All right, so you have the same NMOS channel now, I mean NMOS transistor. So we take the bulk, source, drain, all of them connected to ground, take the gate, but now we start putting a positive voltage, okay? So we slowly vary this positive voltage. So this is VGS, which is with respect to substrate or the source, they're all the same. And now in this case, what happens is, as you slowly start increasing this voltage here, so obviously more positive charges get accumulated on this side of the gate, right? And negative charge, but because this is a P substrate, the substrate won't allow it to have negative charges till the potential goes to a certain point. Now that point happens to be a certain VGS, which is equal to the threshold voltage called VTN. And that's what we define as a threshold voltage. Now it's not a 1 and 0, it happens very slowly. And somebody asks in the beginning, what's the subthreshold region? Actually, the subthreshold region is right before this VTN. So you can still function it as a transistor. In fact, your gain is the maximum in that, but the channel charges are not formed yet. It actually operates more like a BJT. So after this, VGS goes higher than, so if I draw a graph here, let's say, and let's say this is the magnitude of the charge being accumulated on the gate or the substrate side, and let's say this is the gate to source voltage or the gate to substrate voltage. So the charge is pretty much going to be 0, and like I said, it's going to be very small, and then slowly it'll increase linearly. Okay, and this point, the VGS, where it starts increasing, we call it the threshold voltage, which is VTN. For NMOS, for a PMOS, it'll be the opposite polarity, and it's usually called VTP. And now this slope is nothing but your capacitor slope. So it'll be Cox times the area of your transistor. So that's how it looks like a capacitor. And this QI, the expression for this, you can write it as Cox times WL, but VGS minus VT. Okay, so it's only after the VGS crosses VT. So before VGS minus VT, it looks like negative charge, but there is actually no negative charge here. So this equation is valid only after VGS is greater than VT and or just VT. All right, and this voltage here, is referred to as your V effective, VGS minus VT. And you have to remember this. I mean, obviously this is very easy, but you have to remember this. In your design, this should be just like your KCL, KVL. You always will be talking about V effective, V effective, V effective. So this is a very important expression to remember. Obviously easy one, but very important one to remember. So you'll be using this a lot in your design. And essentially what it means is, what is the excess voltage above VT? So a lot of times some literatures or books, they'll refer to this as V on. Some of them will refer to as V OV, which is over voltage, but they all mean the same, right? So make sure you understand what V effective is. So this is a pretty important, simple but important expression. Because a lot of times people think V effective is VDS for saturation, or V on is that, but it just simply means whatever gate to source voltage you have, how much it is above the threshold voltage of that transistor. Okay, so far everyone is good, or you have any questions? All right, I'll just keep going. If you have any questions, like I said, just speak on the mic or just explain it on the chat window. All right, so now obviously so far I've just shown you it as a 2-terminal device, but it's a 4-terminal device. So obviously we want to use the rest of the terminals too. So this, okay, great. So, okay, we want to show the rest of the operation. So now I showed you how the channel is formed, very simply. Now, obviously, once the channel is formed, you want to conduct current with it, right? So you can use it as a capacitor, like as I said before, but mostly what we use the MOS transistor is as a switch or a amplifier device. So we want to see how um, current is conducted through this. Now, so for that, we'll keep the source and the substrate 0, but we're going to add a very small volt VDS, which is also the VD substrate, which is very close to 0. Okay. And we'll try to find out what the current flowing through this is. Let's call that the drain current ID. So if I just draw it with the symbol like before, so I give some VGS. Again, this is VGS positive, and the VGS obviously has to be greater than the VTN. And then I apply a very small drain voltage, VDS, very close to 0, let's say. And I want to see how the current is flowing, right? Because if there is a charge here and I put a potential difference, you get an electric field across this, right? So if there are electrons in electric field, they'll drift. And they'll drift in this direction as positive electrons, and you'll get a current in this direction. Now that current, and obviously, it's beyond the scope of this discussion, but that current ID is actually proportional to the charge density of that channel charge times W over L times VDS, proportional to. By the way, I don't know if I made it clear, but so the L is this distance here. I think everyone probably knows by now. So that's your length of the transistor from the drain to source. And then if I draw the 3D version of this, that gate, this is going to be your W, right? So essentially this current is proportional to the charge density, which obviously makes sense because if you have a certain charge density, you put electric field, your current over time is going to be proportional to that charge density. And that makes obviously sense. Again, this W over L is nothing but resistance, because as you keep increasing this L, your resistance increases, which means that the current will decrease. As you increase W, your resistance actually decreases because you have more area now for the electrons to flow. That's why your current is going to decrease. And obviously it's directly proportional to the electric field, which is direct, in this direction here. So that's the expression. And if I write the whole thing, then ID equals to mu n, and this is the proportionality constant, right? That's the proportionality constant, and that's called the mobility of the transistor. So that's the mobility. And typically that's for NMOS, for most CMOSs, it's between 100 to 600 centimeters square per volt second. And so the higher the number, the faster the device. So if you want to build faster devices like faster gates, faster amplifiers, you want higher mobility. So that's very critical. Now Qn from the last expression, I can write it as, and it's charge density. So the last expression I said it's C aux times W times L, but because it's the density, it's just C aux times the effective voltage, which is VGS minus VTN, and then times W over L times VDS, right? So that's your expression for the current when VDS is very small. So if I just quickly draw this thing. So you can see this current is actually proportional to the gate source voltage too. And then obviously proportional to some physical parameters and technological parameters. So these two are technological parameters because once you get the technology, this is fixed. You can't change mu1, mu-aux, but you can obviously change W and L. So this is under your control. So you can make a resistor which is smaller as you increase the W or bigger as you increase the L, or you can control it through electrically through this voltage here. So if you look at the time responses for a certain VGS1, it'll look linear for a very small amount of voltage. As you increase the VGS, it'll go higher and higher, right? So let's say this is VGS1, this is VGS2, this is some VGSN, where VGS1 is less than VGS2 and so on, then your current goes higher and higher, which means this resistance is smaller than this resistance here. So what you get is a voltage control resistor. So a lot of times in a circuit, wherever we need a voltage control resistor and we know that the VDS is very small, we can actually use this transistor as a resistor, okay? So that's one region of operation where we can use this. Now, what happens if you start increasing the VDS? So, for example, now we take the same NMOS and we apply the same VGS. Let's say that's your VGS. And now what we do is we make the VDS larger. We don't keep it closer to 0. Now, what happens is this channel density, which was pretty much uniform before, it'll start tapering, right? It'll start tapering like this. So basically on the near the source side, so the way this is biased, obviously this is your source, this is your drain, and that's your obviously your gate. So the source side will have the maximum channel density and the drain side will have the least channel density. Now I'll quickly show you a good way to visualize this, why it happens, okay? So I can take this, right? Let's say I draw it as a long, really long transistor, just for clarity, for visual sake, right? I can just draw it like this. So that's a long transistor. Now, this is the drain, this is the source, that's your gate. Now I can take the same transistor and actually split it into many transistors, right? So I'll split them into smaller transistor. So let's say this L was 10 micrometer. I'm just taking as an example. So I'll divide them into 10 where each L here is 1 micrometer. This L is 1 micrometer. The W's are all the same, right? And I'll do like 10 of these, let's say. And all these gates are connected. So this is broken here. So this is same as this guy, just that this drain source are like superconductors. They're just joined like as if there is no resistance, because usually typically this drain and source, they'll have that P plus type and all that, but in this case there's no P plus here. So this is just for argument's sake, okay? Now let's assume that these are small enough that the drain to source voltages are small. So let's say this is ground and let's put some gate voltage, let's say 1.5 volts here. And let's put the drain as 1 volt here. And let's say VTN is 0.5. So this is excess voltage of 1 volt, right? Now, obviously for these small transistors, these are all sources, right? Because you have 1 volt here, you have 0 volt here. If I divide them into 10 equally, so this will have 0.9 volts, this will have 0.4, this will be 0.3, 0.1, you get the idea, 0.2, 0.3 here, right? So you can see that the gate to source voltage here is 1 volt, so the channel will be pretty heavy here. The gate to source voltage is dropped by 0.1 volts, so this will be a little bit thinner channel. The gate to source voltage here only is now 0.8 volts, so it will be thinner. By the time you get to here, the gate to source voltage is almost 0, right? So that's why you can see the channel kind of tapers like that, right? So that's a kind of a way to visualize why you why you get this tapered channel. Now, once you get this tapered channel, this current now is given as mu n Cox W over L. You still have the VGS minus VT, but it's a square relation times VDS minus VDS square over 2. So now it's a nonlinear. This is no more linear. It doesn't look like a resistor anymore. It's a nonlinear equation, right? It's a nonlinear equation. And I'll show you in the next graph, like once I draw the IV characteristics, which region this falls into. Okay, all right. So now once this channel gets pinched off, like as I showed in the previous slide, let's say for example, I had 1 volt here. Sorry, I had 1 volt here. The channel gets almost pinched off, right? So as you see over here, if the the drain to gate voltage here, so if this voltage here, drain to gate voltage, it gets VDG is greater than minus VTN, this channel completely pinches off. So when it pinches off, that means the current doesn't stop, but the current gets saturated. It doesn't increase anymore. So you pretty much get a constant current. So after some time, it doesn't increase with VGS anymore. That's because the channel over here gets pinched off because of the reason I just explained before. Because if you just look at this tiny part here, the gate to source voltage here, because every little channel here is like a small source. So this source voltage, gate to source voltage is less than VTN, which means there is no channel here, right? Now, what it means is that because you have a channel here, but no channel here, but you have electric field. So these currents will go through the electric field. You'll still have conduction, but it will be a constant conduction, right? So now you'll have ID, which is equal to mu n Cox W over L VGS minus VT square. So you can see the VDS term is gone here. Now, if I draw the IV characteristics of this now for the whole MOS, so let's say this is VDS and this is ID. So for given VGS, if you keep the VGS constant, and like as we said, it's linear for small VDS, and then it's after a VDS value of greater than V effective, which is the VGS minus VT number before. And the reason for that is because this channel at that VDS becomes 0. Then from here onwards, it becomes constant, right? Its ID is constant. And from here to here, it's a nonlinear equation, right? So this is your constant equation. This is your linear resistor equation, which we showed before. And this is the nonlinear equation before, the nonlinear part, right? And this is for given VGS. So let's say some VGS1. And if the VGS is lower, kind of going to look like that. So this is from VGS2, which is less than this guy, and so on. Some VGSN, right? Now, this part of the curve, what do you think it looks like? Which ideal element does it look like? We did that last lecture. It's a constant current source, right? If you remember constant current source, like the name says, it's a constant current. Obviously, here it's a constant current source after a certain VDS value, but no matter, it's a constant current source. So actually, that's how we use it as a current source. We'll see a lot of our designs, our analog designs will depend on this fact, and we'll be actually using it as a current source, okay? So you can see that, we used it as a capacitor, a linear resistor, a nonlinear resistor, and a current source. So kind of, because in IC design, you just have these transistors, you don't have the flexibility like in board design where you can get separate current sources. You just have a few minimum devices, and with that you build everything, right? So anytime you get responses like that, you have to exploit them. So this is one of the way we exploit it. Okay, so now the thing is that it's really not constant, exactly constant. Now what happens is, like before I showed that this channel really pinches off, right? And so let's say at VDS equal to V effective, that's when the pinch off happens. That's where you get constant. But what happens after that? Like what happens as I keep increasing VDS above this voltage? What happens is, because now the voltage closer to drain was pinched off. Now the voltage closer to source will get pinched off, and it'll start traveling. But it'll travel at a much slower speed, but the pinch off will travel. So in other words, if this was your channel, let's say this was your source and drain. So let's say you first had this pinch off here, you increase the voltage, the pinch off will decrease, and it'll keep doing that. Now, the L which I showed in the current equation, ID equals to some constant times W over L, right? This L is your L effective, which is basically what is your channel length, not your physical length, but your channel length. So that's this length here, L dash. So if this length is decreasing, that means this current is going to increase, right? So as your voltage is increasing, this effective length is decreasing, which means that this current is increasing. So if I draw the IV characteristics again, just for one VGS, so this is VDS again, and that's your ID. So we said, it starts becoming constant, but it actually is not constant, but it starts increasing, right? I've exaggerated it, but this slope is usually very small if your impedance is pretty high. Kind of increase like that. So now the equation for this is, with the increase, is same mu n C ox W over L times, VGS minus VT square. But now you get another term, which is 1 plus lambda times VDS minus V effective. So essentially what this term is actually gives you the slope of this curve here. And this is nothing but a certain R, right? So when we say output impedance of a transistor, that's really what it is, because it looks like just like as I said, it looks like a current source. And I showed you a Thevenin equivalent of a real current source is you have some R naught. And that's essentially what it looks like, because in real life, you don't get ideal current source. So that's your actual equation. And I think probably a lot of you have solved some of the output impedance problem where you take the lambda and calculate the RDS and so on. And in the next lecture, I'll go into the small signal model. I'll introduce the incremental analysis and go to the small signal model in the next one. Okay, so is that clear? Okay.
So how the gate to source voltage is getting decreased towards right in the 8th slide?
Say that again, can you repeat it?
So how the gate to source voltage is decreased towards right side in the 8th slide?
Oh, okay, let me maybe draw that slide. Yeah, I'll just explain it in a new slide. Okay.
It's 8th number slide.
You're talking about how these gate source voltages are decreasing, right?
Yes.
Yeah, so I'll just show you with another slide, just fresh slide. So like as I said, if you just take this channel, right? And that's your source node. I'm just exaggerating this. That's your source node. That's your drain node. And this is your gate. Now, this is not a superconductor. This channel here, which is a p-type channel which gets inverted, right? It gets inverted. It's not a superconductor. It actually looks like a resistor. So if I draw it, actually it looks like this resistor, right? Now, let's say these were 10 resistors. I put 1 volt, 10 equal value resistor. I put 1 volt, I put 0 volt here. These are 10, let's say I've drawn what? 1, 2, 3, 4, 5, 6. So let me break it here. Okay. So assume it's 10 resistors. What is the voltage going to be here in this channel here? They're all equal value resistors. What is this voltage here?
0.9.
Yeah, exactly. So 0.9, and this will obviously be 0.8, and this will be 0.1, right? This will be 0.2 and so on. Now the gate to source in a channel is not a discrete value, it's a continuous value. So all these nodes are actually gate to source. All these voltages are gate to source. These voltages are gate to source. So let's say I give a gate voltage of 1.5 volts, like I said before, and VT is 0.5 volts, right? So what's the gate to source voltage of this tiny little transistor here? It's not 1.5 anymore, right? It's 1.4 because it's 1.5 minus 0.1. Sorry, 1.5 minus 1.1, which is 1.4, right? So if this is gate to source voltage for this tiny little resistor is 1.4, the channel density is going to be higher than this transistor, which is now 1.5 minus 1.2, which is 1.3. This is 1.2, this is 1.1, and this is 1.5 minus 0.9, which is 0.6, which is only 0.1, 100 millivolts higher than the VT threshold, which means the channel will be really, really thin here, right? So it's a continuous channel. You know, we actually lump it together as abstraction, but it is always a continuous channel. Now, obviously, for very small channels, it kind of looks almost continuous. I mean, abstracted, but it's really a continuous channel. So because the channel voltage is changing gradually, it looks like as if this small source, like this 10 sources, which we have for 10 transistors, which the way I have drawn. So like I showed before, I can actually draw this as 10 little transistors like that, right? And I showed before that Qn is actually proportional to V effective, right? So if all this gate has the same voltage, 1.5, this is 0, this is 1 volt, right? So the effective voltage for this tiny transistor is what? 1.5 minus 0.5, which is 1 volt, right? So Qn is proportional to 1 volt for the first transistor. Let's call this M1. Let's call this M1, M2 to M10, the small transistors here. And for M2, it's proportional to what, 0.9 volts. So obviously this is less than this voltage here. For M3, Qn is proportional to 0.8 volts and so on. And when you get to M10, the V effective is only 0.1 volts. Is that clear? Yeah. So is that clear now? Okay.
Yes, sir.
Good. Okay, good. All right. So, okay, just quickly want to mention about regions of operation. I think in the beginning of, before I started the lecture, somebody asked about subthreshold. So we said, you know, VGS greater than VT is where we operate our transistor, but it's not a 1 and 0 operation. It's actually gradual. So usually when we say subthreshold, that means our VGS is typically in the order of 100 millivolts lower than but it's a little bit more complicated, and you can go into the device physics for this. And for saturation region, which we call the active region, so that's usually it's called the weak inversion, because the channel hasn't completely inverted. Is weak inversion, and this is where we operate the subthreshold. And for VGS greater than VT plus 100 or 200 millivolts, this is not like a hard fast rule because it's very gradual depending on how you operate it. This is called the saturation. Oh, sorry. That's for the VDS. This is called strong inversion. A lot of time people just say active region. Okay. And in between this is just called moderate inversion, right? So just remember this, there's nothing like quantifying here. So when we start designing, it'll become more clear. Like when you want to operate in saturation, active, or subthreshold, it'll be more clear. It's just enough to know. Okay, now I'm just going to quickly talk about body effects. So we said, so far what we've been doing is, like in case of an NMOS, for example, we take the bulk and we've been shorting it to the source node, right? So if you look at the source to bulk voltage, it's been 0. But that's not true all the time. Like for example, let's say you have a switch. So this might be connected to ground, your bulk might be connected to ground, but this could be at a certain potential, like some voltage Vs, this could be at a certain potential Vd. And that's your bulk node. So which means that, and like as I said before, this is always a higher voltage. In case of an NMOS, higher voltage than this, and let's call this voltage source to bulk voltage, which always has to be positive, like I said before, otherwise you'll forward bias that diode there. If you have greater than 0, then the VTN, which I showed before, is not is a different expression now. So usually it's VT0 plus a coefficient called gamma, and this is called the body effect coefficient. It's called body effect coefficient times, I think it's root over VSB plus Pf, and this is again a physical, it's a constant connected to Fermi level, but you don't have to worry about it. Just take it for granted for now. So this is 2 Pf, and this is 2 Pf gamma times this. So when VSB equals to 0, this term obviously becomes 0, and you just get VT 0, which is all the time when for this case. So for this particular case here, VTN is VT 0. And for cases where VSB is greater than 0, you just have to remember that VTN increases, okay? And, usually you don't have to calculate this. We just use a simulator to figure out how much VTN has increased, but you have to be aware of this. So that's the only thing I wanted to point out. All right. Okay. So I think that's all I wanted to talk about the large signal analysis. There's some things which are not clear, it's fine. If fundamentally something is not clear, definitely ask me. But as you start doing design, it'll be more clear. But I just wanted to give you an overview of the large signal analysis. Now, for the small signal, I know, like I said before, you have done small signal analysis a lot, but I'll give you a little bit of motivation and give you a little bit of insight into why we do the derivative, right? What's the reason we do derivative of this, and what is the prime reason we use small signal modeling? So the prime reason we use small signal modeling is to linearize a nonlinear model, right? Like for example, what if we have seen so far? Like for example, this is actually a nonlinear model because the current varies depends on as a function of VDS. So that's a nonlinear model, right? So anytime you have a nonlinear model, you can obviously write the whole nonlinear equation, solve it through iteration and all that. But there are two problems with it. First of all, it doesn't give insight into it. And second thing is that if you want to do quick hand calculations, it just gets very difficult to do it. So I'm going to cover real quickly, hopefully another 15 minutes or so, just give you a motivation behind it and how the small signal comes through it. And then in the next lecture, we'll talk about the small signal model of the MOS and go through the problems, basically. Okay, so what I did was, there is a great lecture at the OpenCourseware at MIT. If you've ever been to the OpenCourseware site for the MIT, they have lots of good resources. I'll definitely encourage you guys to go there. Specifically this course is the 6.002 Circuits in Electronics. It's a basic course. You guys will enjoy it. It has a lot of the lecture notes, videos. This is by a MIT professor named Ananta Agarwal. So definitely take a look at it. So I actually kind of stole this example from his lecture site because I think it's a good example to sort of bring out the incremental analysis. So here's the example. So the example is you get a LED light and you're trying to transmit music signal through it. So that's the example he takes. And so what you do is you apply, so let's say this is a voltage source, which is this music signal over here. So that's your music signal. And this is the voltage source, which signifies your music signal. And it's applied across a LED, right? It's a light emitting diode, which is just simply a diode, forward bias diode. And this voltage is applied across through this. And this current going through the diode is actually emitted as light because it's LED. It could be infrared, it could be visible, but that's. And on the other side, you have a diode, but it's a detector, right? So the light is proportional to this current. That current gets into an amplifier and you get music out. So that's the idea. Now, there's one problem with this. So like as I said, VI gets converted to the diode current, and the diode current gets converted to light, which gets converted to the receiver side and the sound. But one problem here is this conversion here from VI to ID, it's a highly nonlinear process, right? And the reason is nonlinear because you're all familiar with this diode curve here, right? So so that's your diode current equation. So if I write the diode current equation, it's some saturation voltage, and it's exponential of the voltage across the diode over the thermal voltage, which is constant for a given temperature, right? So that's obviously nonlinear. Now, if you're applying AC voltage across it, like, so I'm going to show here. So let's say this is the range of the AC voltage which is getting appear across the diode. So let's say, instead of the music signal, I'm going to just take one tone, which is, let's say, a sine wave, right? So it's a sine wave, which goes like that. Now, you can see that because it's not, okay, so that's, well, it's not a very good sine wave, but you get the idea. I have a little animation also later on. So because of this is, you can see the lower part of the cycle is actually compressed and the upper part is not. So you kind of going to get, some signal like that. So what you get is basically a distorted signal, right? So I'll show you a little animation in the next slide. Just created a rough animation. So basically I've taken this sine wave here, and what I'm showing is that the current which gets ID, you can see this blue dot which is transforming as it is going, it's getting converted to that current. And if I just take this transfer function here, that is sort of the path it is going to follow, and you're going to get distortion, right? So how do I get rid of that distortion? So if you look at this region, probably, like look at a very small region here, right? It roughly looks linear, right? So if I can take this signal, compress it to this region here, then my output will roughly be linear. That's the idea, right? So essentially what you do is you put a DC offset. So instead of putting the entire voltage across this, you actually put a DC offset here. Yeah, put a DC offset, at this region, and then you put your sinusoid signal here, and you should get a roughly linear signal over here. Because for a very small region here, it should look linear, and I'll show a little bit math towards the end. So that's how you would bias it. So you would put a DC bias, so that's your DC bias. So this is your DC bias VI, and this is your small signal. So this is the small delta VI, and which is appear across the LED. So this small signal will result in your light, and hopefully that's linear enough that it will get converted over there. So this is the same picture again, sort of signifying that. So that's the bottom line of small signal analysis. Okay, so these are the very important 3 points you have to remember when you're doing small signal analysis. The first thing is that you operate it at a DC offset, right? So you operate it at a certain DC offset. That's your bias point. So in our particular example, that sets your operating DC voltage across it, which sets the current flowing through it, right? Now on that DC offset, you apply a small VD on top of this VD so that this is roughly linear. That's the whole premise of doing small signal analysis. That then the response ID to this VD, or it could be any other electrical term, is approximately linear, right? And when I say approximately linear, what it means is that it depends on your circuit. Like for example, if you have an audio circuit and you require like a high fidelity amplifier, then you want it to be linear, very linear, like 80 dBc linear. But let's say you're transmitting a 1-bit signal, then you don't need that to be that linear. So when I say approximately linear, and that's what will decide how far a small signal model can be used for a given input signal strength. So again, very important to remember that the response is different for different bias points, right? So you do a small signal analysis for a bias point. If the bias point changes here, you do the small signal analysis again because it's nonlinear. If it was linear, then you don't need to do that again, right? All right, so also a little bit math on why we do the differential. So hopefully this example will kind of motivate you to remember that. So I'm going to follow this notation as it's followed in the lecture in the 6.002 course. So basically, I of capital D means the entire small signal. So that's the entire transient signal, which actually composed of the DC signal plus the small signal. And when we are doing math, I'm going to write this as delta ID just to show that it's an increment above this ID. Okay. So so because it's a nonlinear circuit, ID is nothing but it's a nonlinear function of the voltage which is applied across. In our case, it's the diode, right? So this is a nonlinear function. So we do small signal only for nonlinear circuits. If it is linear, you don't have to because the value of that particular element remains the same throughout, right? So you don't have to do that. Okay, so that's ID. Now, if I substitute VD with this VD with delta plus the increment voltage, so that's the increment, that's why it's called incremental analysis. Then, now for nonlinear analysis, when this is very, very small, what is a mathematical tool you guys use? Taylor series, right? Taylor series or Maclaurin series, but we'll use Taylor series here because the nature of the problem. So which means that if you guys remember the Taylor series, this ID, which is the DC bias plus the incremental ID, is equal to this nonlinear function's output for that given DC bias, right? Plus what's called the first coefficient of the first differential, which is df VD over dVD evaluated at VD equals to VD. This is the most important thing, like as I said before, right? And times delta VD, then plus the second differential, which is D square F VD over dVD, again evaluated at that DC point, VD square, and all the higher terms. Now, because we're assuming that VD is really small, these terms, all the higher terms, we neglect it, right? Now, if you do that, you can see that this term here equals to that, right? Because the DC voltage is nothing but the DC current is nothing but the response of that nonlinear function to this DC. So which means that the incremental part, remaining incremental part is df VD over DD evaluated at VD equals to VD times the incremental voltage. Sorry, I should be using, I think I said, okay, I'll just use capital D here. Okay, so that's your linearized function. So now you get an incremental ID, which is actually a constant, right? So this is a constant because it's just a derivative, times the delta VD. And this is your small signal factor. And in this case, this is nothing but your 1 over resistor of that diode, let's say, right? This derivative term. So essentially delta ID is your one equivalent, that diode in that DC bias region, and delta VD. So essentially what it has done to you is converted that nonlinear in that region with just an equivalent linear resistor. And that's the beauty of the small signal. But like as I said, you have to be very careful when you're analyzing it, because if this VD becomes large, then obviously this approximation is not valid anymore, right? So everyone follows still here, right? And I'll show a quick graphical representation of it. So essentially what you've done is you've taken this nonlinear function here. You've taken this nonlinear function, sorry. So you've taken this nonlinear function here around this point, the bias point, and you've linearized it, right? You've linearized it here. And you can see that this is the real function, but that's your linear, so this is all your error. That's your error. That's your error here. Okay, sorry, just let me erase this one here. So essentially what we've done is we have taken this curve A and approximated with B. And it's only valid for small v because this is the reason it's valid. As you go further away, your error starts increasing. And like as I said, depending on your circuit, that error can be tolerable or non-tolerable, right? So I won't go, maybe I'll go real quick here. So if I just do the same equation, so we had ID equals to, for the diode, we had IS times e to the power VD over VT. So in this case, that first term, the resistor term, is going to be dVD by dt, which is IS over VT times E over VD over VT, right? And that's your 1 over R diode. And if you remember this quantity here, sorry. So I'm just going to write it again. This is nothing but ID over VT. And that's your equivalent to, or I can write as the R diode, the resistance, the small signal. Maybe I should write it as small. So R diode is nothing but VT over the DC bias current. So if you know your signal is really small for a diode, you can just use this expression and you can find the small signal response to it. Okay. All right. I think I'll just stop the video here and then we can discuss if it is